We continue the topology playlist as we still consider foundations for topology. So we have to, get the foundation right so that when we get into the flow, it will be clear what exactly we are in for. So in the last video, I talked about mathematical logic, which was a very comprehensive look at everything about logic, things like how to prove theorems and things like that, approaches and all that. So another important thing we need to do to get ready for topology is set theory. Though on this channel, I have a whole playlist on set theory, like I broke it down in bits. So, but what I'm doing here is actually this set theory, as we get ready to study topology. So, all in one video, I have the whole idea of set theory compressed. So let's go ahead looking at this. Set theory is one of the fundamental languages of modern mathematics. It provides a precise way to describe collections of objects and forms the basis for relations, functions, algebra, analysis, topology, probability, and much of modern mathematics. The lesson develops set theory systematically through sets, subsets, power sets, Cartesian products, relations, equivalence relations, partitions, functions, injections, surjections, bijections, and throughout the lesson, we'll use definitions, examples, proofs, and Python demonstrations where they are useful. So let's go ahead and just go and talk about what sets are. I mean, this is pretty simple. I'm very sure that if you're seeing this is probably not your first time of coming across the idea of sets, because I mean, even in high school, you would have seen it. So a set is a well-defined collection of distinct objects. The objects belonging to a set are called its elements or members. So sets are usually denoted by capital letters such as A, B, and C, while elements are often denoted by lowercase letters such as A, B, and C, small a, B, C. For example, set A can contain elements 1, 2, 3, 4, and 5, means that A contains the elements 1, 2, 3, 4, 5, and we write 3 is an element of A to mean that 3 is an element of A. If an element is not in a set, we can write 7 is not an element of A, like this. So in A, we have 1, 2, 3, 4, 5. So 3 is an element, while 7 is not an element of A. Then we have ways of describing sets. So there are two common ways to describe a set. We have the roster or tabular form. So the elements are listed explicitly. So you have set A and yeah, that's 2, 4, 6, 8, and 10. But that's a roster or tabular form. So you list out everything explicitly. Whereas you have the set builder form, the elements are described using mathematical notation. For instance, this same set 8 containing 2, 4, 6 up to 10 now is actually you can describe it as the collection of all x which are natural numbers where x is even and x is less than or equal to 10. So basically, you're saying that set A is a set of all even numbers from uh, all even numbers from the beginning to 10. Basically, that's what this is saying. Equivalently, you can also say that A is a collection of all x that is natural, such that 2 divides x, that is even number. That's what that means. 2 divides x, and x is less than or equal to 10. So as far as there's any number that 2 can divide and it's not greater than 10, then that's the set you have here. So by interpreting this, you end up coming to the roster or tabular form at the end of the day. So the roster form is convenient when the set has relatively few elements, while set builder notation is particularly useful for describing large or infinite sets. Imagine this is here, we just have 5 elements, so it's easy to just list everything else. Imagine you have 10,000 elements here, or you have 1 million elements, which is possible. So you could just come here and just say, oh, x is a natural number where 2 divides x, and x is less than or equal to 1 million. So instead of listing all the 1 million, maybe not 1 million, maybe 500,000 elements or so, you can just use that simple notation to describe that. So roster form is good for few elements, and set builder form is good for when you have large number of elements. So important types of sets then. So we have the empty set. A set containing no element is called the empty set, and it is denoted by this sign, or this one now. Then, for example, A, which is a collection of all values of all x such that x squared plus 1 is equal to 0. This is empty because there's no x that satisfies this. Because even when x is 0, for all real numbers, even when x is 0, you still get 1. So no x satisfies this. So this is an empty set because no real number satisfies this equation. Thus, we say that A, of course, the only number that satisfies this is complex, and we are talking about real numbers now. So because the collection of x, real x, right? So no real number satisfies this, only complex. So thus we say A is empty, like that. That's an empty set. Then we also have what we call a singleton set. So a singleton set is a set containing explicitly one element like that. So a set containing exactly one element is called a singleton. For example, if A contains only seven, then we say this is a singleton set of with element seven. Then finite set now. So a finite set is a set containing finitely many elements. A set containing finitely many elements is called a finite set. So, for example, no matter how many it is, you can list all the elements, every element. So, A is 1, 2, 3, 4. So its cardinality is 4. So this symbol, which is like what the modular sign we are used to, absolute sign we are used to, it's like magnitude or the number of elements in this set now is 4. So you have 4 elements here without repetition, by the way. Then you have infinite sets. A set containing infinitely many elements is called an infinite set. For example, the set of all natural numbers. What's the last natural number? Nobody knows because it keeps going. You can think it is 10 trillion or 100 quadrillion, and that's not true. That's not the end. So that's an infinite set. It keeps going. Then talking about cardinality, I mean, we've already come across the idea of cardinality right here. The cardinality of a finite set is the number of elements in that set. So if A is A, B, C, D, E, so the cardinality of A is 5 because it contains 5 elements. And the beautiful thing about sets is the repeated elements do not increase the cardinality of a set. So if you have 10 A's and 50 B's and 3 C's and 25 D's and 88 E's, it is still 5 elements because no repetition. And that's why when you come into Python, right? If you are learning Python, you discover that sets are data structures that if you want to preserve, if you want to avoid duplication like that. So for example, you have 1, 2, 2, 3, 3, 3. This is just same thing as 1, 2, 3. So the cardinality of this set is simply 3 because it contains 1, 2, and 3, no matter how many times you repeat any of the elements. So cardinality becomes particularly important when comparing finite and infinite sets. So you can get finite cardinality for finite sets, and for non-infinite sets, it becomes a bit more challenging. So then we talk about equality of sets. Two sets are equal if and only if they contain exactly the same elements. So formally, set A equals set B if and only if for every x, there exists, I mean, for every x, right? X belongs to A implies that X also belongs to B. So for example, 1, 2, 3 is 3 to 1. So the order in which elements are listed does not matter. However, 1, 2, 3 is not the same thing as 1, 2, 4 because there's a difference here. So the sets are different because 3 belongs to the first set but not the second, like this. So the idea of equality of sets also is more like the biconditional thing we saw under mathematical logic, that P if and only if Q, so that is also only true when P implies Q and Q implies P. So A is equal to B in set theory means uh, all the elements of A are in B and all the elements of B are in A, like that. So we have that. Then talking about equality of sets, let's set A be 1, 2, 3, 4 and set B is 4, 3, 2, 1. Are A and B equal? Of course, 1, 1, 2, 2, 3, 3, 4, 4. Even if we have more than any of the repetition of some of the elements, they are functionally 1, 2, 3, 4. So they are equal. So both sets contain exactly the same elements, 1, 2, 3, 4. Therefore, A is B. So now consider C, which is 1, 2, 3, 4, 1, 2, 3, 5. So since 4 is an element of A, but 4 is not an element of C, then A is not equal to C. A is not equal to C, yeah? So the key lesson is that the order of elements does not matter in the set, and repeated elements are ignored. So no matter how you are, whatever the order is, it doesn't matter. So we have for Python now, using Python to define set. So imagine set A 1, 2, 3, 4, 5, set B 4, 3, 2, 1, and set C 1, 2, 3, 5. So to print A, print B, and print C. So if you print these ones now, Python arranges it for you. So then you also want to print this logical statement. Is A equal to B? Then we know if it is true or false. Is A equal to C? You know if it is true or false. So when we run this, you see then that by the time it's all out, so this is set A is 1, 2, 3, 4, set B is 1, 2, 3, 4, and set C is 1, 2, 3, 5. Though this was scattered, it has been arranged here without having to do any special thing. Then now the relationships now is A equal to B. This is what this statement is about, and it is true because A and B are basically the same. Is A equal to C? That's false because this element 5 and 4 makes the difference in A and C. Then we talk about subsets now. A set A is a subset of B if every element of A is also an element of B. So we write that A is a subset of B. Like this equality means, I mean, it means A, even when A is equal to all the elements in A are also in B, A is still a subset. The only thing is that in that case, it's an improper subset. So formally, we say A is a subset of B, implies that for every X, for every X, X belonging to A implies X, that this same X belongs to B. For example, let A be equal to 1, 2, and B is 1, 2, 3, 4. Then we say that A is a subset of B because the elements in A are also contained in B. So this is because every element of A also belongs to B. Then we have the idea of proper subsets, right? So if A is a subset of B and A is not equal to B, that means A and B are not equal. But the elements, you have some elements of A in B, like the one we just saw now. So, and A is not equal to B, then we say A is called a proper subset of B. So in this case, you can see A is a subset of B, but A and B are not equal. So A is a proper subset of B. In that case, we don't need this equality that sign under that. So we then write that A is a so this means A is a proper subset of B. So that other part that looks like equality is out because A is not equal to B. So we remove that part. So for example, we can say that 1, 2 is a proper subset of 1, 2, 3. Whereas 1, 2, 3 is a subset, is simply a subset of 1, 2, 3. Like that. And it is true. While 1, 2, 3 is a subset of 1. This is false because 1, 2, 3 is not a proper subset of 1, 2, 3 because every element here is also here. So this and every element here is here too. So this is false. This is true and this is false. This is a subset. 1, 2, 3 is a subset of 1, 2, 3, but 1, 2, 3 is not a proper subset of 1, 2, 3. Though 1, 2 is a subset of 1, 2, 3, like that. So every set is a subset of itself clearly. So A is a subset of A easily, but not A is not a proper subset of A for any reason because they contain exactly the same elements back and forth. So the empty set is also a subset of every set. So for every given set, two sets are subset, the set itself and the empty set, they are subsets of that set. So we're going to see that probably when we talk about power sets. So identifying subset now, let A be B. Let B be 1, 2, 3, 4, 5, and consider A is 1, 3, 5, and C is 1, 2, 4, 6, and D is empty. For A, right? Every element belongs to B. So 1, 3, 5, you can find 1, 3, 5 here. So that means A is a subset of B. In fact, A is a proper subset of B. So you can remove the equality. Then for C, 2, 4, 6. So you have 2 and 4 in B, but 6 is not there. So you can say C is not a subset of B just because of that 6. And for D, which is empty, D is an empty set. So every empty set is a subset of every set, right? So every set has a subset that is empty, right? So for D, which is empty, and the empty set is a subset of every set. Hence, D is a subset of B also. In fact, you can say it's a proper subset. Then we have membership versus subset. A common source of confusion is the difference between membership and subset notation. Consider A equals 1, 2, 3. So we have 2 is an element of A because 2 is one of the elements in A. But 2 is an element, not a set, right? 2 is not a set, it's just an element. On the other hand, if you have set 2, so this brace makes it a set. This is just a number, this is a set. So this is a singleton set of 2, which is also a subset of A. So 2 is number, is element, and this braces, 2 in braces, is a subset like that. Is a set, which is a subset of A here. So however, we can also say that set 2. So okay, we cannot say that set 2 is an element of A. No, this set 2 is a subset of A, not an element. And this 2 is an element of A, not a subset of A. Very important to distinguish that. So this is false because the elements of A are 1, 2, and 3, and not the set 2 itself. Therefore, X is an element of A means X is an element of A, while X is a subset of B means every element of A is an element of B, like that. So we can do Python subsets here. So we have set A 1, 2, 3, 4, 5, B 1, 3, 5, C 2, 4, 6, and D is an empty set. So this is how you declare an empty set. So print B is a subset of A. So we want to check the truth value of that. B is subset A, C is subset A, D is subset A. So if you run that, you discover that yeah, B is a subset of A. Clearly so. True. C is a subset of A. Not true because 2, 4, no, 2, 4, and then 6 is not there. So that's false. D, which is empty, is a subset of every set. So that is also true like that. Then we have power sets. Now, this is another concept. The power set of a set is the power set of a set A is the set of all subsets of A. So every possible subset of a set you can get forms the power set. So it is denoted by power P of A. Thus, P of A is the collection of all B such that B is a subset of A. So the power set always contains the empty set and the set itself. So these two are automatic members of the power set. So every other subset lies somewhere between these two extremes. So that's what a power set is. So imagine, let A be 1, 2. So the subsets of A are the empty set and 1, 2 itself. Then the singleton set 1 and the singleton set 2 are also subsets. So the power set of A would be the empty set, the singleton 1, the singleton 2, and the set 1, 2 itself. That set A itself. So in this case, the cardinality of this power set is 4 because it has 4 subsets. So the cardinality of that power set is 4, like that. So talking about the cardinality of a power set in clearer terms, so if a finite set A contains n elements, then its power set contains 2 raised power n elements. Therefore, the cardinality of a set A implies that if the cardinality is equal to n, the cardinality of A is equal to n implies that the cardinality of the power set is 2 raised to power that n. So imagine this one now. The cardinality of A is 2. The cardinality of the power set is 2 raised to power 2, which is 4, as you can see there. So the reason is that each element has two possibilities when constructing a subset. So you include the elements, you exclude the elements. Then for n elements, there are therefore 2 raised to power n possible subsets. Now, let's talk on another example on power sets. Imagine this power set ABC. So since the power set of the cardinality of the set A rather is 3. So the cardinality of the power set is going to be 2 raised by 3, which is 8. So, and as we know, for this ABC now, there are two automatic members, the empty set and the set itself. So every other one can now go. So you have the singleton set A, singleton set B, singleton set C. The set of the pair AB, the pair AC, and the pair BC, and so all of that in between. So if you count 1, 2, 3, 4, 5, 6, 7, 8, that's it. So if given the cardinality of a set A to be n, then the cardinality of the power set will be 2 raised to power the cardinality of it. So in essence, what we are saying is that the cardinality of the power set of A is equal to 2 raised to power the cardinality of A. In essence, that's what that is about. So, the power set contains 8 elements, like we've seen here. So we can actually do this here. So we have using Python. So for my to import combinations. So we want to have possible combinations there. So A is 1, 2, 3. So the power set is the set of all the combinations for R in range, the length of A plus 1. So for combination in combination, AR now. So you print the power set. So for subsets in power sets, you print subsets. So print number of subsets, and we have all of that going. So when we run this, you see the power set contains the empty set, then it's 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. So the number of subsets is just 8 right there. So then we talk about Cartesian products. So a Cartesian product of sets A and B is the set of all ordered pairs AB such that A belongs to A and B belongs to B. So it's more like you want to match. I think when I did the set theory example, I talked about maybe you want the Cartesian product of two restaurants. Okay, let's say there are 5 individuals and there are 3 restaurants. So in how many, so maybe you want to see all the possibilities of the 5 people going to the 3 restaurants. So in that case, you have every member of the group matched to every restaurant like that. So that's the idea of cardinality, Cartesian products. So it is written as A cross B. So formally, A cross B will be the collection of AB such that A belongs to A and B belongs to B. And here, order is very important. So the word is ordered. The word ordered is important because it has to be ordered pairs. So that means AB is not equal to BA, actually. So the word ordered is important because AB is not equal to BA in general. So talking about Cartesian product, now imagine this. You have set A, which is 1, 2, and set B is X, Y, Z. So then A cross B will be 1X, 1Y, 1Z, then 2X, 2Y, 2Z, basically. So, and for a Cartesian product, the cardinality, if the cardinality of it, so here, cardinality of A is 2, cardinality of B is 3. So it means that the cardinality of the Cartesian product is the product of the two cardinalities, which is 6. So the cardinality of a Cartesian product is the product of the cardinalities of the subsets making up the sets rather making up the Cartesian product. So order matters in Cartesian products. In general, A cross B is not equal to B cross A. For example, if A is 1 and B is 2, then A cross B is 1, 2, whereas B cross A is 2, 1. So that order is really important. So since 1, 2 is not equal to 2, 1, then AB is not equal to B. A cross B is not equal to B cross A. So this ordered pair structure becomes fundamental when defining relations and functions. So that relationship is really important. So we can do Cartesian products using Python. So from item to import product. So A is 1, 2, and B is AB. So in this case, Cartesian product is the list of the product between one set A and set B now. So then you print A cross B. So for pair in Cartesian products, then you print the pair. So in that case, you have 1A, 1B, 2A, 2B, and that's exactly what you have here. So the cardinality of this is 2. The cardinality of this is 2. 2 times 2 is 4. So you have 1, 2, 3, 4 like that for Cartesian products. And that takes us to the concept of relations. A relation from a set A to a set B is any subset of the Cartesian product A cross B. So in this case now, you cannot, relations are in connection to Cartesian products. So if you want to so a relation from a set A to a set B is any subset of the Cartesian product A cross B. Thus, a relation, every relation is a subset of the Cartesian product. So if AB is an element of the relation, we may write that A relates to B. So a relation tells us which elements of one set are related to which elements of another set. So let's see what that looks like. So for a relation, let A be 1, 2, 3, and B is AB. So consider a relation 1A, 2B, and 3A. Normally, the Cartesian product in general will be 1A, 1B, 2A, 2B, 3A, 3B. But this one just contains some of those elements. So the Cartesian product is 1A, 1B. 1B is not here now. 2A, which is not here, then 2B is here. 3A, which is here, and 3B is not here. So this is a subset of the Cartesian product. So automatically, this is a relation like that. So this is a relation of A to B, from A to B. So since the relation is a subset of the Cartesian product, then R is a relation from A to B. And the relation tells us that one is related to, so it tells us that one is related to A, two is related to B, and three is related to A, like that. So a relation is a R is a relation from A to B, like that. So we have that. So talking about relations on a set, when a relation is from a set A to itself, we have R is a subset of A cross A. So such a relation is called a relation on A. So for example, define a relation R on Z by A related to B. So if and only if A is less than or equal to B. So thus a relation on Z, a relation on the real integer integer on integers, right? Because every ordered pair in R belongs to Z by Z. So relations on the sets can have important properties such as reflexivity, symmetry, antisymmetry, and transitivity, right? So let's talk about properties of relations, this reflexivity and all that we talked about. So properties of a relation, let R be a relation on a set A. So we have property like reflexive. R is reflexive if for every A belonging to A is related to A. A is related to A. So for every element must be related to itself. Then it is symmetric. If so, R is symmetric if A is related to B implies that B is related to A. That's symmetricity. Then so whenever A is related to B, then B must also be related to A, like that. Then antisymmetric, R is antisymmetric if A related to B and B related to A implies that A is equal to B. All right. And then it is transitive. R is transitive if A is related to B and B related to C implies that A is related to C, like that. That's transitivity. So A relates to B relates to C. That means A relates to C itself. So it's more like A is a friend to B and B is a friend to C. So A is a friend to C. That's the idea of transivity. Now, we have how to test a relation. So define a relation R on Z by A related to B if and only if A minus B is even. So reflexivity tells us for every integer A, all right, so A minus A is 0, because this is the definition. A minus A is 0. So since 0 is even, then we say A is related to A. Therefore, we can say that R is reflexive, like that. Then um symmetry. So suppose A is related to B, then A minus B is even, right? So since B minus A is equal to minus A minus B, so B minus A is even automatically. This is just a negation of that. So B minus A is also even. Therefore, B is related to A. Thus R is symmetric in that sense. So I mean, based on this definition that A is related to B, if and only if A minus B is even. So symmetricity works. So for transitivity now, suppose A is related to B and B is related to C. Thus, A minus B and B minus C are even. So Therefore, A minus C is equal to A minus B plus B minus C. So if we work all of that out, so this is even, this is even. So everything is even. So hence, A is related to C. Thus, R is transitive. Therefore, R is reflexive, symmetric, and transitive in that case. Then we talk about equivalence relations. So an equivalence relation is a relation that is simultaneously reflexive, symmetric, and transitive, just like the relation we just looked at. A is related to B if and only if A minus B is even in that case. So therefore, R is reflexive. I mean, so an equivalence relation is a relation that is simultaneously reflexive, symmetric, and transitive. So if R is an equivalence relation on A, we often write A is an equivalence relation, uh, you know, on to B instead of A relates to B. So A relates to B, but then if all these conditions are met, then we can change it to this tilde sign. So A tilde B. So thus, an equivalence relation satisfies A related to A for every A belonging to A, and A relates to B implies B relates to A, and A relates to B, B relates to C implies A relates to C. That's what an equivalence relation is. So we talk about congruence modulo N now. One of the most important examples of an equivalence relation is congruence modulo N. So for integers A and B, so A equals B mod 9n. So it means if you divide A by n, the remainder is B. So this means that n divides A minus B like that. So for example, 17, I don't know okay, let me even, maybe I can have a peep. Okay, it's called, okay, equivalent, right? Yeah, I think it's equivalent. So we have 17 equivalent 5 mod 6. That means when you divide 17 by 6, of course, the remainder is 5. So because 17 minus 5 is 12. So, and 6 divides 12. So congruence modulo n is an equivalence relation on Z like that. So, and then we have congruence modulo 3. The other example is congruence modulo n. So for congruence modulo 3, now define a relation on Z by A is equivalent to B. So if and only if A equivalent A yeah, A is equivalent to B mod 3. That means so if we consider 147 and 14710, then we have that 1, 1 divided by 3 is 0, remainder 1. Then 4 divided by 3 is 1, remainder 1. So the remainder is what we focus on. So this is still remainder 1. 7 divided by 3 is 2, remainder 1. 10 divided by 3 is 3, remainder 1. So 1 is equivalent to 4. 3 is equivalent to 10. All of them are equivalent in modulo 3 because if you divide all of them by 3, the remainder is always 1. Therefore, these integers belong to the same equivalence class. Similarly, if we have 258, 258 modulo 3 now. So the three equivalence classes are 0, 1. So divide 3 by 2, you have 0, remainder 2. Divide 5 by 3. Divide 2 by 3, you have 0, remainder 2. Divide 5 by 3, you have uh 1, remainder 2. Divide 8 by 3, you have 2, remainder 2 also. So the equivalence classes are, so for 0 you have -6, -3, all that. 1 you have all this. 2 you have all of this also. Then these classes divide the integers into 3 groups according to their remainder modulo like that. So when you divide any number by 3, you either have, so for the perfect number that divide perfectly, you have 0. Then the other ones are 1 and 2, like that. Then we go on to talk about the idea of partitions. A partition of a set is a collection of non-empty subsets of A satisfying two conditions. First, the subsets are pairwise disjoint, and then their union is the entire set of A. So suppose we have a set P, A1, A2 up to AN. Then P is a partition of A if AI is not empty. First of all, it is not empty, and for every I, and then the intersection of AI and AJ is not empty. Is empty rather, where I is not equal to J. So, and then if you take their unions, you get your A back. So that's the idea of partition. So the subsets are pairwise disjoint. Pairwise disjoint meaning their intersection is empty. Then their union, the union is the entire set. So pairwise disjoint and the union is the entire set. So if you take all their union, you get back your set. So let's see how that looks like. So imagine a partition. Let A be 1, 2, 3, 4, 5, 6. Consider P is 1, 3, 5, and 2, 4, 6. Both subsets are non-empty, right? They are non-empty. although they are disjoint because their intersection is empty, but their union gives you back your A, which is 1, 2, 3, 4, 5, 6. Therefore, P is a partition of A. So this set P now is a partition of the original set A. Now we talk about equivalence relations and partitions. One of the deepest connections in elementary set theory is this. Every equivalence relation partitions a set into equivalence classes. Conversely, every partition of a set determines an equivalence relation. Suppose this tilde is an equivalence relation on A. The equivalence class of an element A is this. Now you have the equivalent class of A, which is the set of Lx belonging to A such that X is equivalent to A. So the collection of all equivalence classes is called the quotient set. So A, take away the equivalence, you have the collection of A such that A belongs to big A. For example, congruence modulo 3 partition Z into 3 main classes. You have uh, uh, equivalence class 0, 1, and 2, like that for congruence modulo 3. So it partitions the all integers into 3 classes. And of course, you can be sure congruence modulo 4 will partition into 4 classes, 0, 1, 2, 3, like that. Then we go on to talk about functions now. A function from a set A to set B is a relation. So a function is a relation, more or less. So we say function, which is also a subset of a Cartesian product, such that every element of it is associated with every element, with exactly one element of B. So we write F maps A to B. So the set A is the domain, while B is the codomain. So if F of A is equal to B, then B is called the image. B is called the image of A. So formal definition of a function then. So of course we know how we define functions, in algebra and all that. So formal definition of a function. A relation F, which is a subset of the Cartesian product, is a function. If for every A belonging to A, there exists only one B belonging to B. So this A now, with the idea of Cartesian products, you have different elements. All the elements of set A are mapped to each element of set A is mapped to each element of set B. But to define a function, now we now have a distinction that for every A belonging to A now in the domain, we have only one B belonging to B, right? Such that AB is also the pair AB is an element of the function. Therefore, there exists this sign now means there exists exactly one B. Therefore, a function must satisfy two requirements. Every element of the domain has an output, so every A has an output, but each input has exactly one output. So every A has exactly. So for every A, there's only one output, like that. So if you have for every A and you have two outputs in the codomain, then it is not a function. So a function cannot assign two different outputs to the same input. That's what we see there. So every element has an output, but then every input has exactly one output. A function, talking about a function, an example for function is what we have here. So A is 1, 2, 3, B is A, B, C. So define F1. So if F1, let's say F1 is A and F2 is B, like that. So that is 1 is mapped to A and 2 is mapped to B, and then 3 is mapped to C. If we have that, then we say that the function is 1A, 2B, 3C. Like that is a function. First of all, every element here has an image here, whereas yeah, every element has an image here, and no element has more than one image. That's the deal. So this is a function from A to B because every element A has exactly one image in B, basically. Then we talk about relation that is not a function. So we can have a relation that is not a function. So consider R, which is 1A, 1B, 1A, 1B, 2C. So you can see 1 is mapped to A and B together. So though it's a relation, because it's a subset and it is clearly a subset of the Cartesian products, but 1 is mapped to A and B, so that makes it not a function. It's a relation. It's a Cartesian. It's a relation, but it's not a function. So this is not a function because the input one has two different outputs, A and B. So one is mapped to A and one is mapped to B. So a function cannot assign two different outputs to the same input. Therefore, R is a relation but not a function. This is a relation but not a function. So we have three connecting concepts now. You have Cartesian product and you have relation, which is a subset of a Cartesian product. And then you have a function, which is also a relation, right? But so it means it's a subset of Cartesian products. But the fact is that every element in the domain is only mapped to only one unique element in the codomain, only one output, like that. So we talk about codomain, domain, codomain, and range. So suppose f maps A to B, then the domain is A, the codomain is B, and the range or image is the set of all values actually produced by f. So the range is written like this: f of A equals f of A is a collection of all f of A such that A belongs to A. That's the range. So always f of A is always a subset of B. Therefore, the range does not necessarily equal the codomain. So the range, so just like in the case we have here now. So okay, yeah, okay, that's not a good example. So every element in the codomain does not have to be an output to something in the domain, but everything in the domain must have an output in the codomain. However, the range does not necessarily equal the codomain, right? For example, consider this: we have f which maps real numbers to real numbers defined by x squared. So the domain is R, and the codomain, the domain here is every value of x that is real works here, and the codomain, every value of the codomain is also a set of real numbers. So, but the range now, the range is 0 to infinity, like that. For instance, there's no negative here. So the smallest value you can ever have is 0. That's why it is bounded below, by 0, but above it's unbounded. It can keep going. So any number you take, any real number you take, whether positive or negative, it will always be positive. That's why the least small number you can have, the smallest number you can have is 0, and then it keeps going like that. Therefore, f as a function of R is actually the range 0 to infinity, bounded below and opened above, and it is not a subset of the real numbers like that. So, example 7, understanding a function. So for let f map R to R be defined by f of x equals x squared. Evaluate the function at several points. So f of minus 3 is 9, f of minus 2 is 4, f of 1 is minus 1 is 1, f of 0 is 0, f of 1 is 1, f of 2 is 4, f of 3 is 9. Notice that different inputs can have the same output. So you see my f of minus 3 is 9, f of 3 is also 9, f of minus 2 is 4, f of 2 is 4, f of 1 and f of minus 1, all 1, then f of 0 is 0. Notice that different inputs can have the same output. For example, f of 2 is equal to f of minus 2, which is 4. This tells us that f is not injective on R. F is not injective. We are going to talk about injectivity and all of these things as we go on. So this is just a simple code to define a function that returns x squared. So and get the input minus 3 minus 2 all the way to 3. So for x in inputs, then print f f of f yeah, print x matched to f of x. So for minus 3, get 9 minus 2. So just what we have produced up there, actually. So that's the Python implementation of that. So for injections now, so a function f which maps A to B is injective if distinct elements of A have distinct images. That's injectivity. So that's why injectivity is not here now, because minus 3 is mapped to 9. 3 is also mapped to 9, like that. So that there's no injection there. So for injection, it's 1 to 1. So formally, f of A1 is equal to f of A2 implies A1 equals A2, like that. So if these two are equal, it means that their inputs are also equal. So equivalently, if A is not equal to A1 is not equal to A2, that implies that f of A1 is never equal to f of A2. So an injective function is also called a one-to-one function. So one input match to one output. So the main idea is simple. An injective function has no collisions, basically. So one-to-one. Now, proving injectivity. So consider f which maps R to R defined by f of x, which is 2x plus 1. To determine whether f is injective, suppose f of x1 is equal to f of x2. Then we say that 2x1 plus 1 is 2x2 plus 1. So subtracting 1 from both sides, we have that 2x1 is equal to 2x2. Dividing by 2 gives x1 equals x1. Therefore, we see that f of x1 equals f of x2 implies that x1 is equal to x2. Hence, we say f of x equals 2x plus 1 is injective. So that's a simple way to determine injectivity, like that. Then, for a non-injective function, see what happens. Consider f maps R to R defined by f of x equals x squared. So we have f of 2 is 4, and then we have f of minus 2 is 4. So that doesn't make any difference, like that. So in that case, 2 is not equal to minus 2. So we see f of 2 is equal to f of minus 2, and 2 and minus 2 are not the same. Therefore, we say that f of 2 is equal to f of minus 2, while 2 is not equal to minus 2. Hence, f is not injective. If this happens, then f is not injective. So the function has a collision. So we say that the function has a collision because two different inputs produce the same output. So that's a collision right there. So two inputs producing the same output is a collision. Now we have visual interpretation of injectivity. For a function represented by a graph, injectivity can be tested using the horizontal line test. A function is injective if every horizontal line intersects its graph at most once. For example, if f of x is 2x plus 1, it's injective because no horizontal line intersects its graph more than once. So, yeah, because if you visualize this right on Desmos, let's go to Desmos and see how that works. So, um, so here we have 2x plus 1. So you can see no horizontal line intersects more than once. Every horizontal line intersects with this line just only once, right? So, for example, f of x is 2x plus 1 is injective because no horizontal line intersects its graph more than once. In contrast, for f of x squared now, so for x squared, x raised to power 2, right? So you see this horizontal line meets it here and here. This horizontal line meets it here and here. But for this other one, it's only once that every horizontal line interferes with it. So for this case now, it is injective. So in contrast, f of x is x squared is not injective on R because some horizontal lines intersect its graph twice. For example, the line y equals 4. So you see line y equals 4 here. It meets it here and meets it here also at minus 1, 2, like that. Then so intersect the graph y equals x squared. So at x is minus 1, x equals 2. Then even line y equals 1, line y equals 1 here meets it at 1 and minus 1, like that. So that's not injective. So for injection, right, we have so, I mean, this is like what we did before. So, define a linear 2x plus 1 and x squared like this. And we evaluate on minus 3 to 3. So, we have linear outputs and square outputs. And then we compare the results and you see what happens there. So, for linear outputs, you have minus 5, minus 3, minus 1, minus 1, 3, 5, 9. But here, there's no, so you have minus 5, 5. But here you have 9, 9, 4, 4, 1, 1. So, there's collision. So, linear outputs are unique, which that is true. All the linear outputs are unique, but all the square outputs are not unique because you have repetitions like that. Then that's injection. We've talked about injection. So let's talk about surjection. So a function f which maps A to B is surjective if every element of the codomain is the image of at least one element of the domain. It's not necessary that every element of the codomain is mapped to something in the domain. It's not necessary that every element in the codomain is mapped to something in the domain, right? So that's established. But for a surjection, every element of the codomain, every element in B has at least one element of the domain. So formally, we have for every B belonging to B, there exists A that is also that if there exists an A in A. So every element in B is mapped to something in A. And of course, everything in A has to be mapped in the first place for it to be a function. So such that f of A is B, equivalently, the function of A is equal to B. So we say that a surjective function is also called an onto function. The main idea is that a surjective function does not leave any element of the codomain unused. So for a surjective function, every element of the codomain is used up. So proving subjectivity now, imagine, uh, so consider f maps real numbers to themselves defined by 2x plus 1. So take any y belonging to R. We want to find x belonging to R such that f of x is equal to y. So we solve. So we have 2x plus 1 equals y, and then we say 2x is equal to y minus 1, and x is y minus 1 over 2. So since y is any real number, so divided by 2. So y minus 1 divided by 2 will also be real automatically. Therefore, every real number is reached by this function. Hence, f mapping R to R in that case is actually surjective. So looking at a non-surjective function, x squared also comes in. So consider f map R to R defined by f of x equals x squared. So for every real number x squared is greater than or equal to 0. That's always true. Therefore, the range is from 0 to infinity. So negativity doesn't come in here, right? So there's no negative value. So negative real numbers are never produced by once you square any real number. For example, minus 1 is not a subset of this f of R. Therefore, f which maps R to R is not surjective like that. It's not surjective. So um subjectivity depends on the codomain, right? Subjectivity depends on the codomain. Consider f of x, which is equal to x squared, as a function. F maps R to R is not subjective because negative real numbers are not in its range. So in the codomain, there are no negative numbers. So, however, consider f which maps R to the domain, the codomain 0 to infinity. Now, every element of the codomain is reached. For example, y is greater than or equal to 0. Choose x equals square root of y now. Then f of x will now be x squared equals y. Therefore, f which maps R to this closed, this interval closed below and open above is surjective. So the key lesson, whether a function is surjective, depends on its codomain, not just its formula. So the codomain matters in surjectivity because every element in the codomain has to be used up. Then we come to bijections, which is the combination of injective and surjective. A function is a bijection if it's both injective and surjective. All right. So thus, f maps A to B is bijective if f of A equals 1 is equal to f of A equals 2 implies A1 equals A2. That's the condition for injectivity. And at the same time, every element in the codomain is used up, is mapped to something in the domain such that f of A equals B. So in simple language, the bijection pairs every element of the domain with exactly one element of the codomain, and every element of the codomain is paired with exactly one domain element. So everything is mapped. So it is both, a bijection is both one-to-one and onto at the same time. So proving bijection, consider f maps R to R defined by f of x equals 2x plus 1. We already established that f is injective and f is surjective. Therefore, f is simply bijective. So this means that every real number in the codomain corresponds to exactly one real number in the domain. So inverse functions now. A major consequence of bijectivity is the existence of an inverse function. Because every element in the codomain is used up, then we can always find something for it in the domain. So if f maps A to B is bijective, then there exists f inverse which maps B to A, such that f inverse of f of A is actually A. So for every A belonging to A, and f inverse of B is B. So for every B belonging to B, therefore we say that f inverse composed with f is I of A, I sub A, and f composed with f inverse is I sub B, where I sub A and I sub B are identity functions, you know. So, I mean, we can now talk about that in the context of addition and multiplication. So we have additive inverse, multiplicative inverse, and things like that. Then finding an inverse function. Now, how do you find an inverse function? Let f of x be 2x plus 1. So write y equals 2x plus 1. To find the inverse, just make x the subject and change it later. So y is 2x plus 1. So solve for x now. So subtract 1 from both sides. So you have 1 minus 1 is 2x, then x is y minus 1 over 2. So that means that f inverse of x is simply x minus 1 over 2, like that. So to check the composition now, you have f inverse of f of x. So this is f inverse of x now. So substitute f of x inside here. You know, the f of x is 2x plus 1. So put 2x plus 1 back here. So you have 2x plus 1. 1 minus 1 goes. So you have 2x over 2, which gives you your x back. And of course, it's clear that f inverse of x is always x. Now check the second composition, f of f inverse of x. So f is 2x plus 1. F inverse of x is x minus 1. So you have 2 into x minus 1 over 2 plus 1. And that also gives you x. Therefore, f inverse of x is x minus 1 over 2. Uh, it's indeed the inverse function, because if you compose them together, you get x back. You retrieve your x. So comparing injective, surjective, and bijective functions now. Injective, you have different inputs, have different outputs, no collisions. Subjective, every codomain element is reached, nothing is missed. Bijective, both injective and surjective, so perfect one-to-one matching. An injective function may fail to reach some elements of the codomain. So this is what we mean by all these things now. Okay, an injective function may fail to reach some elements. So imagine we have A, B, C, or let's say A, B, C like this. That's set A. And set B, we have 1, 2, 3 like that. Or let's say we have 1, 2, 3, 4, 1, 2, 3, 4. So for a function to even be established in the first place, so for a function to be established, every element here must have an identity, must have something in the codomain. So this is the domain. All right, this is the domain, and this is codomain. So for injectivity, everything here must be used up. So A is mapped to 1, B is mapped to say 4, and C is mapped to 2. So you see, everything is not used up. So this is injective now. This is injective. So as far as everything here is mapped to something, we are good. The 3 is lying fallow here. No, it's not totally used up. So that is injective. So that's the first thing. Then secondly, a surjective function may have multiple domain elements mapping to the same codomain elements. That's a surjective function. So in this case now, uh, so a surjective function may have multiple domain elements mapping to the same codomain elements. So like the case of is it minus 2, like x squared, when you have x squared, like we had the other time. Imagine you have minus 2, yeah, minus 2, minus 1, 0, 1, 2, for instance. So even let's go to minus 3, and you have 3 here. So this is A now, and this is B. So here you have let's now say you have, so let's say the function is x squared, kind of. This is B now. So, it's possible you have, of course, we have, let's now say you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, like this. So you see, minus 3 is mapped to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So minus 3 is mapped to 9. Minus 2 is mapped to 4. Minus 1 is mapped to 1. 0 is mapped to 0. Then 1 is also still mapped to the same one like before. Then 2. Okay, I want to indicate the second one. I want it to be clear. So 1 is mapped to 1. 2 is mapped to 4. Then 3 is mapped to 9, like this. So you can see there are some elements that are not used up. So 2 is not used. 3 is not used. 5 is not used. 6 is not used. 7 is not used. 8 is not used. So, but the fact that one element from here is mapped to, more than one element here is mapped to one element here. So that makes it surjective. More than one element here is mapped to more than one element here. Uh, More than one element here is mapped to one element here. That makes it surjective. That's the idea I'm trying to drive. So there we see surjective. So a surjective function may have multiple domain elements mapping to the same codomain element. So like minus 1 and 2 mapping to 4, minus 1 and 1 mapping to 1. So a bijection has neither problem. So in a bijection, on the other hand, now we have every element is used up. So for a bijection now, so we just have, let's say 1, 2, 3, A, and then A, B, C. So 1 is mapped to A, 2 is mapped to C, 3 is mapped to B. So everything is used up. So this is a bijection. Bijection. So no two elements here is mapped to one thing here, and then every element here is also used up. So that makes it both injective and surjective. So it's a bijection. So thus we say bijective is surjective plus surjective, injective plus surjective. Then finite sets and bijections now. For finite sets, bijections provide a precise way to compare their sizes. So if the cardinality of A is equal to cardinality of A, then there exists a bijection F which maps A to B. Conversely, if there exists a bijection F which maps A to B, then the cardinality of A is equal to cardinality of B. So therefore, two finite sets have the same number of elements if and only if there exists a bijection between them. Of course, bijection means that every element in A is mapped to every element in B. So each element in A is mapped to an element in B, and there's no leftover. So for finite sets, bijections provide a precise way to compare their sizes. So the cardinality in a bijection, the cardinality of the domain and codomain are both equal, right? Basically. So talking about finite bijection now, let A be 1, 2, 3, and B is A, B, C. So define f of 1 is A, f of 2 is B, and f of 3 is C. So 1 to A, 2 to B, 3 to C. So now two elements of A have the same image. So no two elements of A rather have the same image. So F is injective. Then every element of B is also reached. That is so F is subjective in that case. So because they are both injective, it's both the function is both injective and subjective. We say it is bijective. Hence, bijective. Hence, the cardinality of A is equal to cardinality of B, which is equal to 3, like that. So then we talk about infinite sets and bijections. The idea of bijection becomes especially interesting for infinite sets. Consider the natural numbers n, 1, 2, 3, and so on, and the positive even integers 2, 4, 6, 8, and so on. Clearly, the set of even numbers is not is not a is a proper subset, of course, is a proper subset of the set of natural numbers. However, we define a function f which maps natural numbers to even numbers. So by fn, which is 2n now. So this function is injective because 2n of 1, 2n1 is equal to 2n2 implies n1 is equal to n2. And it is surjective at the same time because positive every positive integer has the form 2n. So for some n belonging to n, therefore f is bijective. Thus, we say that the cardinality of the set of natural number is the cardinality of the set of even numbers. So this is one of the fundamental ideas of infinite set theory. This is interesting. Though it is infinite, but the cardinalities are the same. So for bijection now, we have A is 1, 2, 3, and B is A, B, C. I'm mapping 1 to A, B, 2 to B, and 3 to C, the one we saw before. So we can end up having the cardinality of both to be 3. So we have mapping 1A, 2B, 3C. The domain size is 3. The codomain size is 3. The distinct outputs are 3. So bijective, of course, true. So, summary of the main definition so far. So, we talked about a set which is a collection of distinct, well-defined objects. Distinct in the sense that no repetitions are allowed and they are well-defined also. Then subset A is a subset of B, means every element of A is also an element of B. Then we have power set. Power set tells us that the power set of A is the collection of all sets B such that B is an element of A. And here we say that in every power set, we have the empty set and the set itself as members automatically. And the cardinality of a power set A is equal to 2 raised by the cardinality of the set A. So Cartesian coordinates A cross B is a collection of all the pairs A, B, such that A belongs to A and B belongs to B. So every A is mapped to something in B, basically. And a relation is a subset of a Cartesian product like that. So a relation from A to B is a subset of A cross B. Then equivalence relation, a relation that is reflexive, symmetric, and transitive together is said to be an equivalence relation. Then we talk about partition. So a partition is a collection of non-empty pairwise disjoint subset whose union is the entire set. So a collection of non-empty. So it's more like you break up the set into other subsets. None of them is empty. But when you find their intersection, the intersection is empty. That's why you say it's pairwise disjoint. But then when you take their union, you get back the entire set. That's what a partition is. Then you have a function. A relation that assigns exactly one output to every input is called a function. Then injection, a function with no collisions, that is f of a1 is equal to f of a2 implies a1 is equal to a2. So no two elements in the codomain is mapped to the same element in the no two elements in the domain is mapped to more than one element in the codomain. That's injection. For surjection, that's not true. A function whose range equals its codomain is a surjection. So a function whose range equals a codomain is a surjection. And then for a bijection, a function that is both injective and surjective. Then we then have key theorems to remember. Theorem 1, power set cardinality. If the cardinality of A is n, then the cardinality of the power set of A is 2 raised power n. Then Cartesian product cardinality. For finite set A and B, cardinality of A cross B is equal to cardinality of A multiplied by cardinality of B. For theorem 3, we have equivalence relation partition correspondence. Every equivalence relation on a set determines a unique partition into equivalence classes. Conversely, every partition of a set determines an equivalence relation. So theorem 4, bijection and finite cardinality. For finite set A and B, the cardinality of A is equal to cardinality of B. So if and only if there exists a bijection F which maps A to B, then you have the inverse function. A function has an inverse function if and only if it is bijective. Thus, F is bijective if and only if F inverse exists. And that is true because every element in the codomain is mapped to something, to an element in the domain. Some common mistakes. Mistake 1, confusing membership and subset. If A is 1, 2, 3, then 1 is a member of A, but 1 is not a subset of A. On the other hand, if you have the singleton set 1, So the curly brackets tells us this is actually a set. So this singleton set 1 is a subset of A here. Then mistake 2 is forgetting the empty set. Always remember the empty set. So the empty set is always a subset of every set. It's for every set A. So mistake 3, assuming every relation is a function. A relation may associate one input with several inputs. So a function may not, and a function may not. So for a function, every element in the codomain is mapped to a unique element in the every element in the domain is mapped to a unique element in the codomain. That thing is always confusing me. So, but for a relation, that doesn't matter. One element in the domain may be mapped to more than one element in the codomain. For a relation, a function doesn't allow that. So every every function is a relation, but not every relation is a function. That's the idea here. So mistake 4, confusing range and codomain. So for R belonging to R, f of x is equals x squared. So the codomain is R, you know. So the codomain is R, while the range is 0 to infinity, like that. Then mistake 5, forgetting that subjectivity depends on codomain. So the function x mapped to x squared is not subjective as a map. So R is mapped to R, but it is subjective as a map for R mapped to 0 to infinity, like that. Then mistake 6 is thinking bijection means only one to one. So a bijection must be both injective and surjective. So we have conceptual map of set theory. Then the concepts in this lesson are closely connected. We begin with sets, with then from sets we construct subsets, and we also go on to talk about, so using the idea of sets, subsets of sets, we then talk about power sets, and from two sets we construct the idea of Cartesian products. From Cartesian product we construct relations. Special relations then give equivalence relations. Equivalence relations correspond naturally to partitions, and a special type of relations gives functions. So functions can then be classified as injections, surjections, or when both properties hold, we have bijections. Then central structural relationships are therefore set relations, functions, injections, surjections, and bijections. And equivalence relations lead to partitions. Then we have the final perspective. So for the final perspective, set theory provides the basic language in which much of modern mathematics is expressed. So the progression developed in this lesson can be summarized as follows. We have set, subset, and power sets, and then we have set, Cartesian product, and relation, and with equivalence, relation, and partition. Then functions arise as special relations. So we have function leading to, which can be injection, surjection, and bijection. And the most important conceptual distinction is that injection means no collisions. So no two elements in the domain uh is mapped to the same element. Then surjection, nothing in the codomain is missed. So everything in the codomain is mapped to something in the domain. And bijection means no collisions and nothing is missed. So these ideas form the foundation for later topics such as cardinality, countability, abstract algebra, topology. I mean, this is in preparation for topology for sure. Measure theory, probability, and mathematical analysis. So we have our practice problems. So you can see questions 1 to 10 right in this slide. And then in the next slide, we have so in the next slide, we have 11 to 20. So I'm going to be solving two of this. I'll be solving problems. Let me see. I was solving problems 8 and 20. Problems 8 and 20. So let's go for that. Okay, yeah. Let's see the problem 8 and 20 even right here. So 8 is define a relation R on Z by AR. A relates to B if and only if A minus B is divisible by 5. Prove that R is an equivalence relation, and then we'll be doing 20. Let F, which maps A to B, be a bijection. Prove that its inverse, F inverse, maps B to A is also a bijection, and show that F inverse inverse is F, like that. So let's go for that. So we have problem 8. So define a relation R on Z by A relates to B, which implies that A minus B is divisible by 5. So, and then we prove that R is an equivalence relation. Like that. So we have the solution. So to prove that R is an equivalence relation, we need to show, we must show that it is reflexive, symmetric, and transitive. So for reflexivity, right? So for the reflexive, tells us that for every A belonging to Z, that set of integers, A minus A is equal to 0. And of course, 0 is divisible by 5. So since 5 divides 0, then that means 5 divides A minus A. Therefore, we have ARA. Hence, R is reflexive. R is reflexive. That goes. So we have symmetric. So in that case, suppose A relates with B, then 5 divides A minus B. Therefore, there exists an integer k, an integer k such that A minus B is equal to 5k. So if you multiply by minus 1 gives, multiplying by minus 1 gives B minus A equals minus 5k. So, and then since minus 5k is also divisible by 5, that is 5 divides B minus A, so we are back there. So 5 divided B minus A, 5 divided A minus A. So since 5, so 5 divides A minus B, and then 5 divides B minus A, hence we have symmetricity. Hence, B is related to A. So we started from the fact that A is related to B from here, and we showed that 5 divides A minus B, and we ended up showing that 5 divides B minus A. So hence B is related to A, and we can say therefore R is symmetric. R is symmetric. R is symmetric. Then on the other hand, we want to show, so we have shown reflexivity, we have shown symmetricity. Now we need to show transitivity. So we want to show that there's we want to show the transitive part. So in this case, now suppose A is related to B. Now the idea of transitivity is that A is related to B, and B is related to C, and B is related to C. Then that implies that A is related to C. That's transitivity. So then here, 5 divides A minus B, established. and 5 divides b minus c. 5 divides b minus c. So we can say, therefore, there exist integers m and n, such that, so a minus b, so we say a minus b is equal to 5m, and b minus c equals 5n. So adding these equations, now, we have a minus b plus b minus c, which is equal to 5m plus 5n. So, and we know this is a minus b plus b minus c equals 5 into m plus n. And that's the same thing as b cancels b. So we have a minus c, which is equal to 5 into m plus n. Don't forget, both m and n are integers. So m and n are integers like that. So here now we see that 5 divides 5 divides a minus c, because 5 can divide this here. So we say thus 5 divides a minus c, so that we can then say a relates with c, is related to c. Therefore r is transitive. So we've been able to prove all the 3 conditions for equivalence relation. So we can come for that. Since r is reflexive, symmetric, and transitive, then we say that R is an equivalence relation on Z. So that's problem 8 right there. So let's go for the last one, problem 20. So problem 20. So we let F map A to B be a bijection. So we want to prove that its inverse, F inverse maps B to A is also a bijection, and show that F inverse is equal to F. So solution. So since F is a bijection, it is both injective and surjective. Therefore, for every B belonging to B, there exists exactly one A belonging to A, such that F of A is equal to B, like this. So this allows us to define the inverse function, F inverse maps B to A. by F inverse of B equals A whenever F of A is equal to B. So we first prove that F inverse is injective. So then we go for that. So suppose F inverse of B1 is equal to F inverse of B2. So applying F to both sides, gives F of F inverse of B1 equals F of F inverse of B2. So, and since F of F inverse of B is equal to B, we obtain B1 equals B2. You know, in this case now we obtain B1 equals B2, but the inverse is B1 equals B2. Therefore, F inverse is injective. And that's the idea of injectivity. The idea of injectivity is that F of A1 equals F of A2 implies that A1 is equal to A2. And that's exactly what we have here. That if F inverse of B1 is equal to F inverse of B2, then, you know, we have B1 equals B2 like this. So now we need to prove that F inverse is surjective. So for you to prove bijectivity, we have to prove both injectivity and surjectivity. So we have proved injectivity up here. Now we are going to surjectivity. So in this case, we take any A belonging to A. We take any A belonging to A. Now, since F maps A to B is defined on A. So let B be equal to F of A. Then B belongs to B and F inverse of B is equal to F inverse of F of A, which is equal to A. Thus, every element of A is reached. Every element of A is reached by F inverse. Hence, F inverse is surjective like that. Therefore, we can say then that F inverse is both injective and surjective. So F inverse is bijective like that. So finally, the inverse of F inverse must undo what F inverse does. So then, since F inverse of F of A is equal to A and F inverse and actually F of F inverse of B is equal to B, then the function F satisfies the defining properties, the defining properties of the inverse of F inverse. Therefore, F inverse is equal to F. So this result shows why bijections are especially important. So bijections, right, they establish a perfect reversible correspondence between two sets. And on that note, we come to the end of this interesting video talking about set theory as we begin to we continue to lay the foundation for topology. So again, look at the questions. You have 1 to 10 all clear. Here I've done I've done 8 and 20. So you see 8 to 10. I mean 1 to 10, I've done 8. Then 11 to 20, I've done 20. Let me know how helpful this is for you. And if there's something else left in trials, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for that. If you have not subscribed, what exactly are you waiting for? Why not go ahead right now, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges you find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.